In the last two video lectures, we've looked at how we can use the results from statistical decision theory to obtain Bayes optimal classifiers. And in this video lecture, we'll turn to the regression problem and find Bayes optimal regression solutions. We have three topics for this lecture. The first is we'll formulate the problem, the Bayesian regression problem. Then we'll look at how this solution to this problem gives us the regularized form of the solution for the regression problem. And finally, we'll look at how we can apply what we've learned about conjugate priors to formulate a solution for the problem and the prediction of new outcomes given new data. Okay, let's recall that the way that we formulate a regression is with a response, some y that is the response variable for the problem, and we have a data matrix x. And again, the y is just a scalar value on each individual case, and the x consists of rows where each of the columns in the x matrix is again variables. And we can think about many problems that have this form. You could think of, for instance, measuring the amount of algae pollution in a lake based upon predictors that include rainfall and the chemical composition of streams that flow into the lake. Okay, and we have a parameter which we're going to call theta, and that's the parameters of the regression problem. So our regression then, expressed as in matrix notation, is the vector of y's is equal to the matrix, the data x, times the parameters, the vector of parameters theta, and plus some vector of error terms, which in this case we assume have constant variance and are uncorrelated. The parameters are random variables in a Bayesian formulation. So theta then is a random vector. In traditional maximum likelihood estimates, we just treat the betas or the theta values, which are the parameters in regression, we treat them as fixed, but that we need to estimate. But in the Bayesian formulation, we treat them as random. So this is now a random vector. Okay, given a prior for this random vector, which we'll call P of theta, and data, which again, this is a classic formulation. We have a data matrix and a response vector. Then we can express the posterior in terms of the data that we have. So this is x and y, and the parameters are of course the thetas. So that posterior is on theta given the data, and it's just an application of Bayes' rule. We have the likelihood for the data given the values of the parameters theta, the prior of theta, and divided by the evidence, the probability or the probability density function for the evidence. So typically we know x, obviously that's our data matrix. It's not random. Y is a function of x, made random by this epsilon. So we're going to make our notation a little bit easier and simply write the posterior as a function of y. Although we know that the x values, the data matrix is data that enters the problem space. This will just make our notation a little easier. So what we need to do then is estimate theta. And we can do this because of what we found from statistical decision theory, that if we find the posterior of the theta in this case, and find the expected value of that, and in this particular case we'll find the maximum of it, which is equivalent, and it's known as the maximum a posteriori estimate, then we're going to find the estimate that gives us the Bayes optimal solution. And the approach we're going to take is to use conjugate prior, because this is a very convenient approach to derive the solution here, since the assumptions behind regression are based upon a Gaussian assumption for the model. So let's make a Gaussian assumption for the prior as well. and that's a convenient way for us to go. So when we look here, we have a prior distribution that's multivariate Gaussian with parameters theta naught, or theta sub 0, which is the vector for the prior distribution for theta, and a variance-covariance matrix of both sigma sub theta. The likelihood for the problem, and again we're expressing this in terms of y, it also has the x's of course carried through, but we're expressing it in terms of the y, since these are the values that are really random in the regression problem. Then that's a likelihood given the value for theta and given the error distribution that's on the error in the regression equation, which is defined by sigma squared, in our case sigma squared epsilon. And so the parameters here are x theta, which is the mean of the regression model, and sigma squared epsilon times I, which is the variance-covariance matrix. The I is the identity matrix. So this is basically a matrix with sigma squared I running down the column, or excuse me, running down the diagonal. The conditional posterior then, given what we know about conjugates, since the prior is conjugate, the conditional posterior is conjugate. Of course, we know the marginal is a t-distribution. It doesn't matter because for both of them, the mean is in fact, as we said, the maximum of the posterior distribution. And we can just use the results that we found from our conjugate analysis to directly write down the estimate for the expectation of the posterior mean, and that is as shown. And notice that in it we have, as we've noted before, the influence of the prior distributions through the parameters of the prior, theta naught and sigma sub theta, as it carries through in the estimate of the mean value for the posterior. It's important to note that this Bayesian solution actually acts to regularize the resulting estimate. And to see that, we can look at it directly. If we suppose that the our prior distribution has for theta has a variance-covariance matrix that in fact is also diagonal, given by little sigma squared times I, and that we have a mean of 0 for the prior, which means that we've normalized it. We've made it, we've scale normalized it, so we've put it right around 0. We've subtracted off the mean. Then the map estimate is given by, notice we have another parameter in there, lambda. And that parameter is just the ratio of the two variance components that we have. The one variance component, sigma squared sub epsilon, is the error that is contained within the regression model itself. And sigma squared theta is the error that's contained within our prior distribution. So when we look at this, it should look familiar to you from your statistics class. This, in fact, is ridge regression. And in ridge regression, the solution is given by exactly the same thing. The only difference there is that in ridge regression, we don't talk about what lambda is, but now we have an understanding through this Bayesian analysis that it is in fact this ratio of these two error terms. In general, in ridge regression, choosing the theta actually determines the performance of how we regularize the problem, which means we reduce the number of variables in order to get, or we downweight the number of variables in order to get a better solution, a solution that generalizes better in our problem space, which is what we mean by regularization. So when we look at classic ways of doing this, we're searching with a grid search or cross-validation, that kind of thing, to try and find lambdas. But again, with a Bayesian approach, we now have a basis for understanding what it is that that lambda value is and what it means for the particular problem that we're working on. Now, notice that we got the solution with a classic form of regression, which has a sum of squares. It's ordinary least squares regression, so a sum of squares loss function. We could also think of, however, an absolute loss function. And in exactly the same way that we got ridge regression, the Bayesian solution there would be the lasso regression solution. Now, instead of just the maximum, just finding the estimate for the parameter, we may want to find the entire distribution. Again, this is something that we can do when we use a Bayesian approach to the problem as opposed to a maximum likelihood. So that means we actually have to find the denominator in the Bayesian solution, which is the f of y, or the density function for the data. And we can find that by looking at it in a normal or in a conditioning way, which suggests that we condition to remove the theta values in the posterior and just find the data. And this, of course, is the sum rule, as we saw it, or the conditioning argument that we made early on in order to find the denominator in Bayes' rule. So we can find the posterior distribution by continuing with our conjugate approach. And what we're doing here is we're just rewriting what we assumed about the prior and the likelihood that they're both Gaussian. Again, with the prior parameters theta naught and sigma naught, and the likelihood with the parameters defined by the regression, x theta and sigma squared I. And using that, we can write the distribution for y just based upon the prior, and that regression then would be x theta naught, because those are the parameter estimates that we would use that derived from the prior, and the variance-covariance matrix being altered by the values of the prior variance-covariance matrix, sigma squared, and the data, which is the sum of squares going through that. So the conditional posterior then, with these assumptions, is a Gaussian, and again, these are the parameters derived from the conjugate analysis, with the mean vector for the posterior distribution, the Gaussian posterior distribution given as shown, and the variance-covariance matrix also given. And these values, you can see, have the data within them that's causing them to move away from the prior values that we specified in the prior distribution, now being altered by the data through the data matrix, and of course the variance that we have in the problem. So this gives the complete distribution for the estimate of our parameters. With the posterior distribution for theta, we can now do things like prediction, where we can actually estimate how good the prediction is. So our goal is to predict some new value y given a new x, and I'm showing this as a lowercase x to indicate that we have, for instance, one row in a data matrix that's brand new, and we want to predict the new value for y given that. So from the conditional posterior that we found for theta, we can obtain the value for this prediction of y now with the new value of x. So that's what we want to do. And the way we do that is, again, by conditioning, and the conditioning is using the posterior distribution of theta. And from the regression model, we can derive the first term, of course, as a Gaussian. The first distribution is a Gaussian, just given by the regression parameters. So the distribution from the prediction then is easily found, and to make things a little bit easier notation-wise, let's say that the prior distribution has a variance-covariance matrix that's diagonal. So that gives us then the posterior parameters that are shown. This is the mean and the variance parameter for the posterior distribution that we found, and that then can be used to give us the distribution for the prediction, and that also is Gaussian. And now the parameters are as shown. And notice that the parameters are based upon the posterior parameters that we obtain for theta given the data, and that's how we find the distribution of the prediction.